get started. So this talk will be split into two sections. The first section will be covering some design decisions involved in writing distributed software, and the second section will be looking at control system software specifically. First, a little bit of background about me. I have a fairly diverse background. I've done all kinds of software engineering. Most recently, I'm doing DevOps engineering. Most relevant to this talk, though, is when I worked at the Scarlet Laser facility, which, for those of you who don't go to OSU, is located on the fourth floor of the Physics Research Building on the north side of campus. This is a picture from the first time they fired the petawatt laser. It's kind of hard to see in this room with the projector, but that purple spark over there is air that has been turned into plasma because of the laser firing. I'm standing on the left. The person in the middle is Richard Freeman, the principal investigator. And the person on the right is a coworker who did not get the memo about black collared shirts and crossing his arms. Basically what they did was fire lasers at different kinds of materials and record the results for research purposes. I don't know too much about the research side of it, but they needed someone to write software that would automate different processes for safety and efficiency, also to collect data from all of the instruments in the lab and then analyze it, and to allow the scientists to work with the laser system basically easily. That person ended up being me, so I designed the control system and I worked with a team to implement it, and that's kind of what led to my interest in control systems in the first place and ultimately to giving this talk. So what are control systems? I have a picture here of a car, and the content isn't terribly important. I know it's a little fuzzy, but the gist of it is that a modern car has a lot of sensors and actuators inside of it. Typically, there's an engine control unit, but sometimes there are other controllers as well. And the software running on these controllers collectively would be the control system for the car. So a control system is software designed to control devices, record data, and automate processes. You can kind of break them down into three different categories as well based on what kind of guarantees they make around reliability and response time. So you have hard real-time, firm real-time, and soft real-time. The car is a good example of hard real-time. Basically, if you miss a single deadline, that's considered total system failure. So if you can imagine the airbags deploying late after the crash and not in time for the crash, that would be a total system failure. Firm real-time is a little bit of gray area, but a good example would be an assembly line in a factory where you have like a camera that detects bad widgets coming down the line, and maybe you have like a flipper that knocks the bad widgets off into a bin for QA to look at later. If the system occasionally misses a deadline, if the camera detects a widget a few seconds late and the flipper misses it, it's not the end of the world, but it's not nearly as useful as if it actually did it on time every time. And then soft real time is the most permissive. There are no deadlines, but generally speaking, the slower the system is, the less useful it is. So a good example for that would be home automation. If I hit a button to turn my lights on and it takes 30 seconds instead of 1 second, nothing terrible has happened, but it's not nearly as useful to me. I want to talk about a project I've been working on recently called MDCS, which stands for the Modular Distributed Control System. And the reason I want to talk about this is because during the first half of the talk, I'm going to be outlining different design decisions and trade-offs, and I'm going to be telling you what I chose for MDCS and why. And if I give you a code example, it will also be from this project. So it's a personal project that I'm working on for fun. I don't have a particular end goal in mind, but there are several use cases where it would be useful. Modular refers to the fact that it's made up of several components with well-defined interfaces. The idea here being that you can swap out the implementation or maybe not even use all of the components if you don't need them. Distributed refers to the fact that it runs on more than one computer, kind of like in the title of this talk, distributed software. Also that you kind of try to avoid single points of failure. Basically, the components should fail independently of each other. If you're in a factory and one half of the factory loses power, I should still be able to open and close doors on the other half of the factory. It is a control system. Specifically, it's a soft real-time control system. Hard real-time usually requires some kind of hardware support or running in a specialized operating system like VxWorks. This runs on Linux, so that's not the case here. One thing I want to point out is that most scientific facilities do use control systems. So an example of that would be EPICS, the Experimental Physics and Industrial Control System. It's a bit of a mouthful, but It was developed, I think, at Argonne National Labs and is used, for example, in the Large Hadron Collider. This slide is actually where the project logo would go, if I had one. So for the first half of the talk, we're going to be covering design decisions in writing distributed software. Probably the most important one is serialization. I initially had a lot of slides on this topic, and I took some of them out because I think this is a topic people are usually very familiar with. Having said that, it's something you're going to have to decide on early on in your project's design, and it's going to have a lot of impact on basically every component of it. So some things you want to think about are validation. If you're sending data over the network, or you're storing it on disk or in a database, how do you validate that it is actually correctly formatted or encoded? Versioning, what happens if you change the way an API works, or if you change the way one of your components work? Binary data, sometimes when you're working with hardware, you might be in a situation where you have the ability to get data from the hardware, but you don't have access to the protocols or the proprietary software you need to convert that data into something usable. So a good example of this would be scientific cameras. You can get a byte array out of them, but the actual software you need to convert that byte array into a JPEG or a PNG is proprietary, and it's not something that you might have access to. And then bandwidth and performance are kind of, I think, similar topics. I mean, basically, it comes down to what requirements you have. If you hit a button and you want your lights to change instantly, you want to consider how much data you need to transmit in that amount of time and what kind of performance you're looking for. Some use cases I want to run by you here. So you have simple types, right? You might be working with booleans, integers, strings, whether a light is on or off, the brightness of an LED. You might be working with compound types, though. RGB colors could be represented as 3 floating point numbers. Or you could be working with multidimensional types. So an image might be represented as a 2-dimensional array of RGB colors. So just whatever your use cases are, you're going to want to think about that when picking your serialization library. The problem with serialization standards is that there are a lot of them. And everyone seems to have one. They all work slightly differently. Here's a small selection of them. There are a lot more out there. These are just the ones that I am most familiar with. For MDCS, I ended up choosing Apache Avro. It's not super well known, but it's actually a pretty neat project. It provides schema support, which I think is useful not just for validation purposes, but for documentation purposes. It has native support for working with binary data, which is nice because I have to work with binary data, and I don't want to have to worry about encoding or decoding it into JSON or some other kind of format. It also provides binary and JSON serialization support, though. So if I do want to do that, it handles it for me. OK, interesting. And it also provides client libraries in Python, C, and Java, which are the 3 languages that I'm likely to use for this project. You could probably spend a lot of time searching on Google for different libraries, and new ones are being written all the time. So I wouldn't be surprised if there are other good choices out there as well. Here's an example of an Avro schema. So this is an array of dictionaries that have 3 fields each, which are of type float. You can probably guess by that name that I left in there. I copied and pasted this out of real code. This is a dictionary or an array that represents CPU usage in a multi-core computer. This is about middle of the road. You can get a lot simpler than this. You can just say it's a string, or you can get a lot more complicated than this. And here's some example code. So this is also out of MDCS. It's how you go about encoding a string with a corresponding schema into binary data using Apache Avro. I'm not going to spend too much time talking about the code specifically, but the gist of it is that you hand the schema and the value over to Avro, which then writes it to a byte buffer, and you can get the bytes out of that byte buffer. You could be writing it to a file. You could be writing it to a network socket. It doesn't really matter. This is how I do it in my code, though. Binary decoding is very simple. It's the same thing in reverse. A little bit of magic there because you have to read it out of a data reader, and you have to use a next call for an iterator, but otherwise relatively straightforward. All right, APIs. So you've picked your serialization library, and now you're realizing that you're going to have to implement at least a few APIs for these different software components. Some things you want to think about are client support. Console clients are probably a common option, but also you might be working with JavaScript single-page applications, right? Web browsers, Mobile applications, probably JSON over HTTP or HTTPS is going to have the widest amount of client support. And what's really neat about that is when something breaks and you want to troubleshoot it, I might not be able to install your special client on the machine I'm on. I can troubleshoot it with curl. On the other hand, if performance is a concern, that might not be the best choice. Similarly, data flows are something you want to consider. So HTTP is request response. But you might also have publish subscribe where a group of machines is communicating with only members of its group or other groups of machines. There's push pull, there's a bunch of other ones. And then performance, I mentioned briefly, but if you have performance requirements, you might want to actually have multiple APIs cater to different users of your application. And lastly, documentation. If you're using a schema, which I hope you are, because generally speaking, I think they're good things, I want to see that schema. If you're not using a schema, how are you going to document how your end users are going to use your API? If you do end up making HTTP APIs, one tool you might want to check out is Swagger. It's just swagger.io, but you can Google it. And it lets you document HTTP APIs, but also generate client libraries in different languages, which might be useful if there's a language that you don't want to provide first-party support for, but you'd still like people to be able to use it. So here's an example. One of the components in MDCS is called a node, and it actually has 3 APIs. There's an HTTP API for inspecting and changing settings. So this is a non-performance critical API. This uses JSON over HTTP. There's a TCP API, which is for communicating with connected devices. This is the performance critical one, and it uses Apache Avro binary encoding. And there's a multicast API for network discovery, but also other kinds of event traffic. So this is one of the cool things about Apache Avro is all of this is using Apache Avro encoding, either binary or JSON. Which kind of leads me into network I/O. So I think sockets kind of get a bad rap. I think a lot of people think sockets are complicated, but they are an option. You could also use a third-party networking library. ZeroMQ or NanoMessage are ones that I have experience with. I'm sure you could find others. ZeroMQ in particular I used at the Scarlet facility, and I really liked it. But that was, I think, version 2, and now they're at version 4.x or 5.x. Or you could use a broker. So a broker is basically an external service that handles messages between different components. MQTT is really popular in the embedded space, and RabbitMQ is very popular in sort of like web application development. So the only thing I would say with that is you really want to think about your failure cases. With MDCS, at least specifically, I don't force you to have any kind of like single point of failure. RabbitMQ can be set up in a high availability mode where you mirror queues between different nodes, but if you don't do that, or if you're using something like MQTT, you have to handle that. I mean, what happens if RabbitMQ goes down, right? Does everything shut down, or can some things still work? Similarly, with the brokerless libraries, ZeroMQ, for example, buffers messages on both ends of a connection, which is really handy if you have sort of an unreliable network and the connection can drop and get reconnected. But sometimes it doesn't get reconnected, and if you're not familiar with how it works, it can lead to unexpected failure cases. So whatever you pick, make sure you understand what happens when things go wrong and that you can live with that. For MDCS, I chose native sockets. And I chose those because they're not as complicated to work with as I think a lot of people think, but also they're provided by the operating system, and I didn't want to introduce any third-party libraries or services that I didn't absolutely need to. Part of the reason is because I want MDCS to be approachable for beginners. You don't have to learn about how to use ZeroMQ, which is somewhat complicated. There's a lot of information out there on sockets. A lot of people know how to use them, fairly portable. So here's an example, actually. This class is responsible for reading and writing Avro encoded messages over a socket. I put some imports and stuff in here so you could see it. I mean, it's a stripped down example, but the important part is in the constructor, I create the socket, I connect to the remote server, and then I create a read buffered file so that I can read from the file instead of having to use the socket receive API. In Python, there's a lot of opportunity to use something like sockets and to actually use higher level APIs to work with them instead of having to fall back to whatever the POSIX standard specifies. And this is one example of it. So in read message, framed reader is an Avro class. and I'm handing it the read buffered file, but I could just be handing it a local file or any file like object. Write message, also very similar. I use the socket send API, and to close it, I close the buffered file in the socket. Now, this isn't production code. I stripped these examples down because I didn't want you guys to be looking at like error handling and stuff. So there is some error handling I've taken out of here. But even if you were to use this in production, socket.send doesn't necessarily have to send the entire buffer. It can send a small chunk of it, and then it's up to you to handle replying or retrying. But even if you did that, the read message call here would probably throw some kind of Avro exception. So it's actually not terrible to work with sockets at a pretty naive level. And if you haven't tried it before, I encourage it. Right, so you have maybe you have one component, but I think a lot of bigger projects end up being broken down into different applications. And you have one API, maybe you have multiple APIs for each of these components. There's sort of a question of how do you go about architecting them to make them sane and straightforward to look at. So there's three models. There's the process model, threaded, and asynchronous. I'm not really going to talk about the process one because I don't see anyone doing it very often. It's usually reserved for compute-intensive workloads. So with the threaded model, you open a thread for every single API. You handle one client at a time, or you open a new thread for every single client to that API, and you're using threads. So if I figured out the flickering. It's this little cable on the ground here. So if you end up going with the threaded model, Python 2 and 3 ships with a library called Socket Server that implements base classes that make it really easy to work with sockets that are used for servers. On the other hand, if you go with the asynchronous model, this is where you use an event loop, and you can either use like futures or promises or await async, which is in Python 3. And yeah, Python 3 ships with async.io and AIO HTTP. You could use a single thread, or you could have multiple threads, and this is something that the event loop usually hides away from you. Now, yes, asynchronous model is going to be a little bit more performant, and the reason for it is because you don't have the overhead of one thread per client. So hypothetically speaking, you can scale that a lot better. On the other hand, the threaded model is, in my opinion, easier to understand for beginners to programming. Yeah, you might have to worry about synchronization issues, but in practice, at least in MDCS, that hasn't been an issue so far. So as I just mentioned, that's what I chose for MDCS. Maybe in the future, I might switch to the asynchronous model, but it shouldn't really matter from the perspective of the end users. So here's an example. This is the TCP API server for the node component I showed you earlier. Once again, I'm not going to go too deep into this, but you can see I'm importing the TCP server class from Socket Server Library. I'm extending it. I am passing in the host and port that I want to listen for connections on. A request handler, which is on the next slide. I'm setting bind and activate to false. I'll talk about that in a second, and allow reuse address to true. Allow reuse address is for debugging purposes. You probably don't want this set to be true all the time, but it means that if I stop my software and start it back up again, I don't have to wait for that timeout period that you normally would have to wait before you can listen for connections on the same host and port. So if you can imagine debugging an application, you're hitting Control-C up and then running it again. That's exactly what this helps with. Bind and activate false is putting the responsibility to bind the socket and start listening for incoming connections on me. The reason I'm doing that manually is because this constructor is called as part of setting up the process in the beginning, and then it actually forks a couple of times to run in the background as a daemon, and that's when run is called. If I open the socket earlier, I would have to keep track of it and make sure that it's not closed as part of that process. It's kind of an implementation detail, but you see this pattern throughout the entire code base, and I think through other code bases that have to worry about daemonizing. Serve forever just listens for incoming connections, handles them one at a time, or in parallel if you're using the thread per client model. And then when it's asked to stop, it returns, and I call server close. So there's a bit of boilerplate here, but I don't think it's terrible. And this is effectively the code that I'm using more or less in production. So here's the handler. This is definitely stripped down. A lot of error handling I took out of this. But every single time a client connects and it sends a message over the TCP socket, a new instance of this class is created, the handle method is called, and it provides some conveniences like a read buffered file and a write buffered file, just like I was using earlier. Framed reader, framed writer are Avro classes, so essentially I'm using Avro to pull one message out of the connection. I figure out how I want to deal with that message, and then I use Avro to write the response back. All right. The last networking topic, I think, that we're going to cover is network discovery. I mentioned earlier that I wanted to design MDCS in such a way that it didn't force you to have a single point of failure in your system. One of the ways in which I do this is by having the different components discover each other using network discovery. Now, there's a couple of different ways you can do this. This is some of them. Broadcast is just using UDP broadcast traffic, sending it to the local network broadcast address. Multicast is a publish-subscribe model where it's still using UDP, but the routers on your network keep track of what groups each computer is part of, and then you can send a message to all of the computers in a particular group. MDNS stands for multicast DNS, and it's exactly what you think it is. It's DNS over multicast. Avahi and Bonjour are common client implementations of these. I do believe there's one on Windows as well. I don't use Windows too often, so I'm not familiar with it. And then you could use an external service. You know, network discovery is kind of a complicated topic, and there are entire teams at different companies working on this, or service discovery, which is kind of related. So Consul is a HashiCorp product. You might know them for Vagrant. That's a much more common HashiCorp product people use. And Zookeeper is an Apache project. So pros and cons. Broadcast is a very naive way to do it. You're going to have a lot more traffic, and you're going to waste the time of some of the computers on your network that aren't interested in the network discovery. Also, broadcast isn't designed to leave the local network. So if you can imagine you're maybe at a research facility or a factory, then you have two separate networks on opposite sides of the facility. Yes, there are ways to fudge it, but usually broadcast traffic isn't going to leave those networks. On the other hand, multicast traffic is designed to leave those networks. So assuming your routers are correctly set up, multicast traffic can be used for network discovery across even the internet. On the other hand, end users are unlikely to know how to work with it. You know, if you've ever had to look up what multicast groups a Linux machine is a part of, raise your hand. No one. Yep, I didn't, 2 months ago, I wouldn't have been raising my hand either. It's actually netstat-g, so there you go. You learn some practical things here. So yeah, I mean, who are your end users? Are they gonna know what to do when network discovery doesn't work, right? Also, are the routers gonna be configured correctly? Is this like a small router you bought at Best Buy, or is this a router being run by the Ohio State University, for the purposes of a research department? Multicast DNS, I do not recommend you implement this from the protocol specification. It's actually quite complicated, but if Avahi and Bonjour do what you need to do, then great, you're done. Unfortunately, Avahi and Bonjour are designed for like network discovery of printers, computers, network shares. So they might not actually do what you want them to do. In my case, they don't. I wanted to include extra information about my services that I couldn't. And then lastly, external services. These are even more complicated. I mean, I've set up Consul and I've used it in production. It took me about 2 weeks of reading the documentation to figure out the correct way to set it up. And I'm still finding out ways to improve that configuration. So, if you're willing to live with that, great. If you're not, maybe consider something simpler. Zookeeper I've never worked with, but I've heard good things. I've also heard the documentation is sparse and it's very difficult to figure out what goes wrong when it goes wrong. So for MDCS, I chose multicast. It's still relatively easy to work with. It's using operating system provided primitives, just UDP traffic over sockets. But it's not as naive as broadcast, and it does allow you to do network discovery over more than just the local network. So let's look at an example. If you haven't noticed, I'm using the socket server library in basically all of my examples. And that's because it's a fantastic library. And it does a lot of things. It has a UDP server-based class. I filled this example in with actual values. So you could see the difference between the host and the port that I'm listening for connections on locally, and the IP address that I'm using in multicast to represent a group. So if you're not familiar with multicast, groups are represented by IP addresses in a particular range of IP addresses. This is one I picked randomly. Please don't use it for your own projects. I'm using it for mine. And I don't want to get your traffic in my components. The run function is very similar. I omitted the bind and activate stuff, but before I start listening for incoming clients or incoming connections, I use the socket API to join the group I want to be a part of. This sends out a data packet over the network, and it tells all of the routers that, hey, I would like to participate in this group. And then the routers do the hard work of figuring out when they need to send you traffic. And then before I close the server, I leave the group. It's not strictly speaking necessary. I think these time out by default every couple of minutes, but there's no need to be wasteful with network traffic we're not going to listen to. And I included this here just so you could see that using it is pretty straightforward. If I want to send a message to everyone in the group, first I'm using serialized value, which I showed you earlier, so that exact function. And then I'm using the send-to API, and I'm sending it to the multicast IP address. And then the routers on the local network will do the hard work of sending copies to each of the computers that are a part of that group. All right, 1 minute break so I can drink some water here. The second half of this talk will be focusing more on application of all of the stuff I've talked about, specifically with regard to control systems. All right, in the beginning I mentioned that control systems are useful for controlling connected devices, recording data, and automating processes. And that's true, but probably the most useful thing they do, in my opinion, is they provide an abstract model of the world for your end users to use, right? So if I'm a scientist working with the equipment in a lab, or maybe we can go back to that car example and say I'm the engineer writing the code for the LCD panel in the dash, and I need to decide if I'm going to display a warning that your tire pressure is low. Do I care how the tire pressure sensors communicate with the car, what protocol they use, what frequency they use? I really don't care. I just need to know what the tire pressure is, right? So if your model ends up being too realistic, I mean, it's probably not the end of the world, but you're just going to make life a lot harder for your end users than it needs to be. On the other hand, if it's too abstract, you take the risk of leaving out important details. So for example, the tire pressure sensors in your car only work when the wheels are spinning. So there's a battery in there, and the battery's supposed to last years. So in order to conserve battery power, when the wheels are not spinning, they don't send any information at all. They shut themselves off. So if I'm asking the car what the tire pressure is and it's telling me 0, I might want to know if the car is actually running or not before I go ahead and display that warning to the user. Hey, heads up, you have no tires. So the correct amount of abstraction is just right, which I really like this diagram because it illustrates the point of leaving out an important detail if you go in the too abstract side of things. But in MDCS, sort of the main model I use is this idea of a device, right? So a device has a globally unique identifier. You could call it a name if you want to, but it's an identifier. One or more named attributes and one or more named actions. Attributes sort of collectively represent the state of the device. So we could think of maybe like a connected smart bulb. The brightness would be an attribute. Actions represent subroutines that either change the state or do computation. So if you can think of like those smart home scales, calibrating the scale would probably be an action. Or maybe if it's like a web camera, returning the image in a non-standard image format, converting it from a JPEG to a PNG, that might be an action. Attributes have values. These values are typed using schemas. Actions have parameters and return values. These are also typed using schemas. So let's do an example here. This is an interactive example, so prepare yourselves. How would you go about designing a device to represent this? This is a control panel for a CNC machine, but it really doesn't matter. It's not critical. I don't know how a CNC machine works. So, well, the obvious ones are like the emergency stop button. That would be an action, right? You hit the button and it's over with. You run an action, and that's what you can do. The X, Y, and Z axes would probably be attributes, probably floats from 0 to 1.0. I don't know. It looks like the needle can go from the left to the right side. The lights would be either Booleans, on or off, or integers, if maybe there's like different colors the lights could be. What about the little toggle button you can see in the top right, where it could be in like one of 3 positions? Raise your hand if you think that should be an attribute. One person. Nice. You're passing the class. Raise your hand if you think it should be an action. So, okay, all right. Well, it depends. So I would probably do it as an attribute where the type is an enumeration, and you can pick the different positions as the values of the enumeration. But it might be one of those buttons where you have to push and hold it, and it only does the thing as long as you're holding it, and then when you let go, it releases. I mean, I think ultimately you have to think about who's the end user. What model are they going to expect? Are they a trained machinist who knows how to run a CNC machine? Or is it someone like me who has no idea how to run a CNC machine, but I still want to see it turn on and spin? So here's a real example. This is a screenshot of a web interface I have for MDCS. This is a Philips Hue light. I've blanked out the serial number of my Philips Hue bridge because I don't think it's important that you can control my lights. But what you're seeing at the top there is the actual identifier. So it's Hue dash the serial number of the bridge dash light dash 16. You want your identifiers to be globally unique. Philips Hue guarantees my serial number is globally unique. This is a globally unique identifier, right? I have a list of attributes. You can see I actually have a name attribute that's named kitchen middle. Yes, I have multiple lights in my kitchen. This is the middle one. Some of the attributes can be read, some can be written. For the ones that can be written and that use a very simple type, so that the type of name is going to be string, I actually provide an option here for you to change the value or get the current value. If the type was to be really complicated, like that example I showed earlier where it's like an array of dictionaries, I would probably just say, you can't do it through this web interface. I think there's like a placeholder that says, sorry. One interesting thing I want to point out here is the fact that there is a name and it's different than the identifier. You can get pretty creative with shortcuts that your system takes when your end users are working with it. In my case, in the page before this, it actually shows you the value of the name attribute. So I don't need to remember that it's light 16, I just see kitchen middle. Here is how this is defined in the code. So there's some imports here. Device is the interesting one. It's a light device. I'm passing in a name and some configuration settings. And this is where the name attribute is defined. You can see you can read it, you can write it. The schema is a type string, and I'm passing in a function to read and write the value. Reading it makes an HTTP GET request to the Philips Hue bridge. The result is JSON, and I'm pulling out the name field. All right, last sort of thing to talk about is an interesting application of control systems, which is automation. So in my apartment, this is something I would like to automate. If my phone is connected to my home network, and there's motion detected inside of my apartment, check to see if we're within evening hours. If we are, make the lights brighter and turn on the AC. You can imagine other use cases for this kind of software. Another one that I'm looking into actively is feeding my dog on a schedule. But something I want to point out here is your end users may not be programmers. Or maybe they know how to program, but it's not their day job, so it's not something they're used to thinking about. So maybe you might want to automate things using a flowchart as opposed to using like scripts or an API. Me, I'm a programmer, so the way I solve this is, I wrote a web application that has a REST API, it has a queue for running jobs in the background, it has a database, and I call this a reactor, and a daemon for running these jobs. And basically, that action that I showed here, more light, looks like this. This is a Lua script. I know, it's PyOhio. If you don't know Lua, pretend that colon is a period, and you're basically there. So what this does is it gets a list of devices that match that pattern. So my Philips Hue lights would match this. It gets the current brightness, it computes a higher value, it turns the light on, and then it sets the brightness. Some interesting things I want to point out here is I'm kind of like duck typing devices based on their name and the attributes they have, right? So I might have a light device that doesn't have a brightness attribute. If that was the case, this code probably wouldn't work. I would throw some kind of exception, but in practice, this is one of these things that it turns out it actually works quite well. I mean, for the same reason that duck typing works quite well in Python. All right, and these are some other topics I would have liked to talk about. Access control. The radio in your car should not be able to deploy your airbags, so somehow that has to be solved. Recording attributes. Does the device tell you when an attribute has changed, or do you have to pull for the new value? What happens if you have a device like a temperature sensor that is very precise but not accurate, or very accurate but not precise? I can never keep those straight. And then hot plugging devices. I want a globally unique device identifier. What happens if I unplug it from one machine and plug it into another? If you're interested in control systems, there's a lot that you can read up on, more than just this. But I just kind of wanted to get you thinking about some of the challenges that might be involved in writing software that deals with issues like this. This is my email address. I am looking for contributors to MDCS. It's in what I would call alpha state right now. I'm using it to automate the lights in my apartment, but I have other things that I want to use it for. If you're interested in working on it, feel free to email me, or if you have questions. This is the GitHub repository. This talk is inside the documentation folder of this GitHub repository. I think I have 30 seconds if anyone has a particularly burning question. If not, you can email me later. No? ActiveMQ, if I remember correct, implements AMQP or AMPQ. So ActiveMQ and RabbitMQ implement the same sort of protocol, right? Yeah, I mean, you can do a lot of fancy things with RabbitMQ or any AMPQ library. I've never worked with ActiveMQ, but yeah, it's a good. I mean, it's a valid choice, and if you're willing to live with setting it up and running it, then why not? Anything else? Fairly well. I'm not using it right now in MDCS for readability reasons, but there's basically a mix-in. You import UDP server and threaded server, and you just inherit from both, and it kind of handles it transparently. I think this is going to have to be the last question. Yes. MPI, you mean the library for running code in parallel on a cluster? Network methods. Talk to me afterwards. I was actually wrong. I guess we have 10 minutes, and the time on my presentation wasn't accurate. Well, any other questions? No? All right. Great. I'll leave this slide up for a minute. That's all I have.